Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss the inner product and orthogonal bases. In this topic we will review the dot product and introduce a new notation, the inner product, represented by an angled bracket operator. We will describe orthogonality and again review and the angle between vectors and define the 2 norm of a vector in terms of the inner product. We will describe the projection of a vector v onto a vector u, that is, the best approximation of v as a scalar multiple of the vector u. We'll describe how to approximate a vector v as a linear combination of an orthogonal set of vectors. And we will review the useful properties of the inner product. Now recall that the dot product between two n-dimensional vectors is defined as the sum of the pairwise products with the first vector entry conjugated. Now there is a slight issue with this notation because even though u and v are vectors, the dot product gives a real or complex value. Now, if we look at notations such as vector addition, scalar multiplication, and for 3-dimensional real vectors, the cross product, such a notation suggests that the result is a vector. But it's not. It is a scalar value. Consequently, it's more usual to define the dot product as a more general operation called an inner product, and then rather than using a dot, we have 2 angled brackets with 2 operands. Now, of course, if we are dealing strictly with real vectors, this simplifies to just the sum of the pairwise products. And again, we should remember that the result of the angled bracket operator is a real number in this case. So essentially, the inner product yields a scalar, not a vector. Now, applications of the inner product include the ability to determine when 2 vectors are orthogonal or at right angles. You may recall that 2 vectors are said to be orthogonal if the inner product between those vectors is equal to the scalar value 0. Now, basically what it means is 2 vectors are orthogonal if neither vector contains any information about the other vector. We can also carry on by defining an angle between 2 vectors. The Cauchy-Schwarz-Bunyakovsky inequality indicates that the numerator is less than or equal to an absolute value of the product in the denominator. Therefore, this ratio must be between -1 and 1, and therefore we can take the arc cosine or inverse cosine of this ratio to define an angle, and the inverse cosine of 0 is pi, or 90 degrees. We can also define a distance between 2 vectors. So the 2 norm of a vector is just the square root of the inner product of a vector and itself, which is simply the square root of the sum of the absolute values squared of the entries. Now, the projection of a vector v onto a vector u is the best approximation of v by a scalar multiple of the vector u. So that is, the projection of v onto u is that scalar multiple a times u, such that the distance between v and a times u is minimized. So consequently, the distance between v and and the projection of v onto u is less than any other scalar multiple of the vector u. Now, the scalar a can be found by this expression here, and you can go back to your linear algebra notes to see why this is true. However, we can just use the fact that we are minimizing the 2 norm. So in this case, the projection is just the inner product of u and v over the inner product of u and itself times the vector u. That is, the scalar a is just the ratio of these 2 inner products. Notice that if 2 vectors u and v are orthogonal, then the best approximation of v as a scalar multiple of u is the 0 vector. 0 times u, which is the 0 vector. So that is, there is no other scalar multiple of u that comes closer to v other than just simply the 0 vector. That's what we mean by when we say that 2 vectors are orthogonal if one vector contains no information about the other. Now, if a collection of n vectors u sub 1 through u sub n forms an orthogonal basis for either r to the n or c to the n, that is, n-dimensional vectors, then given an n-dimensional vector, we can define the coefficients a sub k as being the inner product of the kth vector u sub k and the vector v over the inner product of the kth vector u sub k with itself. In this case, the vector v is exactly equal to this linear combination of the orthogonal basis vectors, which is essentially just the sum of the projections of v onto the n vectors u sub 1 through u sub n. And so, since we've calculated the coefficients a sub k, this is just v equaling the sum of a sub k times the kth vector u sub k, k going from 1 to n. Now, interestingly enough, if some of the coefficients are sufficiently small, we can actually discard those terms and still get a reasonable approximation of the vector v. Now, if u sub 1 through u sub n forms an orthogonal set of vectors in Rn or Cn, where m must be less than n, then given a vector v, we can still find these coefficients. However, now that linear combination of the vectors u1 through um is simply the best approximation of the vector v by a vector in the span of the vectors u1 through um. The span, of course, is all possible linear combinations of those m vectors. So, for example, here we have a vector v. We already know that we can write this vector v as a linear combination of these 4 canonical basis vectors, and you will notice that these vectors are indeed orthogonal to each other. The coefficients can be found by calculating the appropriate ratios. However, these 4 vectors, 1, 1, 1, 1, 1, 1, negative 1, negative 1, 1, negative 1, 1, negative 1, and 1, negative 1, negative 1, 1, also form an orthogonal basis of r to the 4. So therefore, using the formula to find these 4 coefficients, we can find that we do indeed have v as being this linear combination of these 4 orthogonal vectors. Notice that the first coefficient is actually quite small. So if we were to discard that first term, then we would find a linear combination of the last three orthogonal vectors. And notice that that is not an exact, or is not exactly equal to the vector v, but it is reasonably close as an approximation. Now, recall the following properties of the inner product. First of all, the inner product of a vector and itself is always a real number that is greater than or equal to 0. And the inner product of a vector u and itself is equal to 0 if and only if the vector u is the 0 vector. This is why we can define the length or 2 norm of a vector as the square root of the inner product of a vector with itself, as the inner product is always greater than or equal to 0. Second, the inner product is conjugate symmetric. That is, if you calculate the inner product of u and v, and then calculate the inner product of v and u, the two values will be conjugates of each other. Of course, if u and v are real, then the inner product is symmetric. Finally, the inner product is linear in the second argument. So the inner product of u and alpha times v is just alpha times the inner product of u and v, and the inner product of u and the sum v plus w is just the sum of the inner product of u and v and the inner product of u and w. These are all the useful properties of the inner product as they are defined for real and complex finite dimensional vectors. Consequently, we're going to be looking at other vector spaces, and we're going to define different inner products, but all the rest of the results will actually simply follow. So following this topic, you have reviewed the dot product and you now are aware of our new angle bracket notation for what we will call the inner product. You have reviewed orthogonality, the angle between vectors, and the definition of the 2 norm of a vector, the square root of the inner product of a vector and itself. You understand how to find the best approximation of a vector v as a scalar multiple of, or a linear combination. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!